Okay, so here we're gonna wrap up this section here. We're gonna talk about orthonormal basis, right, and how that helps us or simplifies finding a basis representation for a vector. Right now, first we're gonna start by just introducing this theorem and then adding to our NME5, right? So kind of showing why or just kind of properties of a basis, right? And a reminder here, a basis has two defining properties, right? So a basis is a spanning set and it is linearly independent. Okay, so it has to satisfy both of those conditions, right? So we could have a spanning set, but it could not be linearly independent, in which case it is not a basis, just a spanning set. We could have a linearly independent set, but it not being a spanning set, right? Now, quick way to think of that, if we think of just these two vectors, let's say this was my vector set. Right, these are linearly independent, right? But we do not have a spanning set, right? So it's not a basis, right? If we can come up with even a spanning set, right? Let's say, for example, here, let's do the standard one. Okay, and then we just add another vector to it. All right, I can clearly see from here that that other vector that I've added to it, I can write as a linear combination of the previous three, in particular the first one and the third one. All right, but it's still a spanning set, right? It still doesn't change that fact, right? I still have those first three, which do span R3. Now that additional one, all it does, it takes away the linear independence, but again, right, still a spanning set, but not a basis, right? So again here, Li, not spanning. And then here, spanning, but not linearly independent. All right, so here we're going to start kind of making our connection here, because as we've seen in other problems, the challenging part here is determining whether a set spans or not. And here we're going to this will lead us into the topic of dimension, which we'll talk about in the next section here. But here, let's take a look at our textbook here to introduce this theorem here. So if we look at theorem, or we're looking at here theorem CNMB, the columns of non-singular matrix are a basis. So here it says, suppose that A is a square matrix of size M, then the columns of A are a basis of C to them if and only if A is non-singular. All right? Okay, so now if we have a non-singular matrix, what this theorem is telling me is that its columns form a basis for whatever the size of it is, right? If it's a 3 by 3, then it's for R3. If it's a 4 by 4, then it's for R4. Now that makes sense, because if you think of if A is non-singular, what does that reduce to? So here, let me get back to the board here. All right, so it makes sense here. Because if A is non-singular, A reduced row echelon forms to I3, right? Or IN, I should say. Right? If that's the case here, well, each one of these is the standard basis vectors, right? Right. Okay, so then we know is in fact a basis. All right. So what this also does now is with that fact, I can now add on to my NME theorem that we've been working on throughout the course here. All right, so now this is our 5th iteration. All right, theorem NME, a non-singular matrix equivalences, round 5. So we're going to add to this, right? A is non-singular, right? So here again, all these are equivalent properties, right? If one of them is true, all the other ones are true. Now we're up to 8, right? A is non-singular. A row reduces to the identity matrix. The null space of A contains only the 0 vector. The linear system has a unique solution for every possible choice of B. The columns of A are linearly independent set. A is invertible. The column space of A is C to them, again, which makes sense since they're Li, right? A row reduces now to I3, so this property should make a little more sense here. And then the columns of A are a basis for Cn. All right. Now it's not a standard basis, right? But it is a basis. Okay. And as we've seen, right, a basis is not unique. Some are more advantageous to use depending on what we're using them for. All right. So now let's talk about some of those different types of bases and why we would use them. All right. Now, if we have this, the most straightforward is the standard basis, right? That one is really easy to use, right? Any other bases would involve solving for a linear system to find the coefficients, right? So what do I mean here, right? So let's say that we had the standard basis for R3. All right, so we have E1, E2, and E3. All right, now if I wanted to write the vector, let's say W, which I'll call 2, -1, 5, right? In terms of the standard basis, well, since E1 is just the vector 1, 0, 0, well, it's just the coefficients, the linear combination are the choices, the elements of this vector here. Okay, so we see here the linear combination of that basis, right, would involve just taking whatever coefficient. The coefficient is just a term in my column vector. Now for another basis, let's say just a random basis. Let's say I had the basis that is okay, now in this case here, this set is a basis for R3, 3 vectors that are linearly independent. All right, so again, in the next section, we'll show why this is enough to show that they're just 3 vectors and they're linearly independent to show it's a basis. But for now, we can take for my word for it, it's a basis. if I were to find the vector representation of W in terms of that basis, what that would entail would be that I would have to set up a system of equations where I'd have to solve for alpha 1, alpha 2, alpha 3, okay, and solve this linear system of equations for alpha 1, alpha 2, alpha 3. All right, so we have to do row reduce again and solve for those terms, which again could be tedious when there is another way, right? Now let's say that I had an orthonormal basis, right? And again, any basis or any set of vectors can be made orthonormal, right, where they're orthogonal to each other and of length 1, right, by the Gram-Schmidt process. All right, so just given any basis, I can do this Gram-Schmidt process and have an orthonormal basis. So as it turns out, if you have an orthonormal basis, you eliminate having to doing any row reduction. And what you have to do now is simply take inner products, which is a much more straightforward approach, depending on the size of your vector space. Oops. All right, what you have now changed the problem to is, instead of, as above, solving some linear system, you just do a dot product, an inner product, right, where the bases here are the vectors v1 to vp, right, and that represents an orthonormal basis. Okay, so for our above example with the vector w given as 2, -1, 5, right, and let's say we had our orthonormal basis consisted of the vectors 0, 1, 0, 1 over root 2, 0, 1 over root 2, and then 1 over root 2, 0, -1 over root 2. Okay, so that is my orthonormal basis. Right. Okay, so if I wanted to find the vector representation here of W in terms of that basis, I don't need to solve a linear system, right? What this theorem tells me, this is theorem COB. All right, so what this theorem states is all I have to do is just find the inner product here of my vector v1 and w. So if I do that again element-wise, so this becomes -1, v2, what does this become? 2 root 2 plus 5 over root 2. And that gives me 7 over root 2. And then lastly, v3 times the vector w. Right, and this becomes 2 over root 2 minus 5 over root 2. And that's -3 over root 2. All right, and now I find my coefficients, right? So then my coefficients, so now W is 2, -1, 5. -1 times 0, 1, 0, plus 7 over root 2 times 1 over root 2, 0, 1 over root 2, plus, or minus, I suppose here, 1 over root 2, 0, negative 1 over root 2. All right, and now notice how this is much faster here than solving a linear system, right? The system above would have required a lot more calculations, right? Now here there is some work that needed to be done up front in constructing the Gram-Schmidt process. Here I was just given to it, but again, if we didn't have orthonormal basis, then we would have to go through the process of finding it, right? Which again, depending on what we're using it for, might be beneficial in just being able to show the vector representation much more easily, right? And you can see here, just to show you that this is going to be correct, multiplying these in. So we got 7 halves, 0, 7 halves. And here, right, root 2 over 2 is just 2, and then plus, let's do here, that's negative 3 over 4, and 0, and then the bottom one is plus 3 over 4. All right, and we could see here, adding these up, the middle one is negative 1. That one's not an issue here. And then up top, we get negative, it should be 2. The top we get 7 minus 3 is 4 over 2, which is 2. And 7 plus 3, that's 10 over 2, which is 5. All right, so we see here, we have a vector representation in terms of my orthonormal basis. All right, and you see how much more straightforward the calculations are to find those coefficients if I start working with an orthonormal basis.